All right, welcome back everyone to the deep dive. You know how this works. We take a fascinating research paper, tear it apart, and pull out the really juicy bits for you. And today we're tackling, well, it's a bit of a head scratcher, honestly. You see, these text-to-video models we've all been hearing about, they're getting insanely good at making things look real, like scarily real.
Oh yeah, it's mind-blowing what they can do visually. You type in pretty much anything and boom, you have a video that could fool anyone.
Exactly. But here's the catch, and this is what today's paper really digs into. How can we be sure these models actually understand what they're showing us? Or are they just creating these super convincing illusions, kind of like, well, a really talented magician?
Right, it's like, are they just learning to associate certain words and phrases with certain visuals without really grasping the why behind it all?
That's exactly the question this paper. VACT, a video automatic causal testing system and a benchmark, sets out to answer. And they've come up with this pretty clever system, VACT, to automatically test whether these video generators are truly understanding cause and effect or just playing a really good game of visual mimicry.
And this is crucial because, we're talking about models that could potentially be used in all sorts of real-world applications, robotics, self-driving cars, you name it. But if they don't actually understand the physics of the world, the underlying cause and effect, and well, things could get pretty dicey.
Oh, absolutely. They give this example in the paper that really stuck with me. They had OpenAI's Sora generate videos of two scenarios, one with a stone being thrown into a swimming pool and another with a feather being thrown into the same pool. Now, both videos showed a pretty big splash, the kind you'd expect from a rock. But a feather...
Yeah, I remember that. A feather's way too light to cause a splash like that. So right away, it raises a red flag. Is the model really understanding the physics of how mass and force work? Or is it just learned that object plus water equals splash no matter what the object actually is?
Precisely. And that's what makes this research so important. Because if these models are going to be used to, say, train a robot or simulate self-driving scenarios, we need to know they're not just showing us what looks right, but actually get the why behind it all.
Completely agree. So VACT, this video automatic causal testing system, it's all about trying to get at that deeper level of understanding automatically without having to rely on humans to go through and check everything.
So how does this VACT system actually work? Like, what's going on under the hood?
So the basic idea is pretty elegant. They take some concepts from causal analysis, how we figure out what causes what, and combine them with the reasoning power of a large language model, or LLM. The goal is to basically set up these experiments, they call them intervention experiments, to see if a video generation model really understands cause and effect.
Right. And they start by defining what do they call it? A causal system for a specific scenario. Like, let's stick with our pool example. They break the system down into two parts: a causal graph and structural equations.
Well, think of the causal graph like a simplified flowchart of how things work in that scenario. You have different variables, which represent all the things that could be happening, and arrows connecting them to show what causes what. Then the structural equations are like the rules, the if this, then that logic that the model's supposed to be learning.
I see. So for our pool example, you'd have what they call root variables, which are like the initial causes. So things like how dense the object is heavy or light, how fast it's thrown, fast or slow, and how big it is, large or small.
And these root variables then lead to other things happening, what they call non-root variables, which are basically the effects. In our case, it could be whether the object sinks, if there's a visible splash, if there are ripples in the water, even things like if the water sparkles. The arrows in that graph would show, that if something's dense, it'll probably sink, or that a dense, large object thrown fast is likely to cause a big splash.
Right. And to keep things simple so the system can easily pick these things out in the generated videos, they treat all these variables as Boolean, meaning they're either true present or false absent. Makes sense.
It does. Now, here's where things get really cool. They use a large language model to automatically create these test scenarios and those underlying causal systems.
Wait, so the LLM is like the test designer?
Exactly. You give it a test description of a situation, like something is thrown into a swimming pool, and it acts like a smart assistant, figuring out all the key factors, the possible outcomes, and how they might be connected.
Wow. So it builds that whole causal graph we talked about, figuring out how everything's related, and then even comes up with the Boolean expressions, those if this, then that rules.
You got it. And here's the kicker. The system has all these checks built in. So if the LLM creates a rule that doesn't make sense or isn't formatted correctly, the system flags it and prompts the LLM to fix it. It's like having a built-in quality control for causal reasoning.
That's wild. So the LLM is basically learning to think about cause and effect on its own.
In a way, yeah. And get this, they actually compared these LLM-generated causal systems to ones that humans made. And surprisingly, the LLM did a better job at making sure the root variables were clear and independent and that the rules made sense.
No way. That's incredible. So the LLMs are getting pretty good at this logical reasoning stuff.
They really are. Okay, so once they have this causal system set up, the ACT moves on to actually testing the video generation models. And they do this through what they call an automatic intervention experiment pipeline. It's a mouthful, I know.
Break it down for us. What are the steps?
Sure. So first they do what's called sampling. Basically, they select a bunch of different combinations of values for those initial root variables. Like in our pool example, they might try all the different possibilities of heavy light, fast slow, large small.
Gotcha. So they're trying to cover a good range of different initial conditions.
Precisely. Then comes prompt generation. They use another LLM to take those combinations of variables and turn them into actual text prompts that are fed to the video generation model.
So instead of just something is thrown into a pool, you might get prompts like a large rock was thrown quickly or a tiny feather was gently placed on the water, that kind of thing.
Yep, that's the idea. And then, of course, comes the actual video generation step, where the model takes those prompts and creates the videos. Importantly, VACT treats these models as black boxes, meaning it doesn't look at how they work internally. All it cares about is the final output.
Okay, so the focus is on the results, not the process. What happens next?
Next up is answer retrieval. Here they use what's called a vision language model, a model that can understand both images and text to watch the generated videos and see what actually happens. They do this by asking simple yes or no questions, what they call probes, about the state of those variables, like did the object sink, was there a noticeable splash, that kind of thing.
And I'm guessing the final step is comparing what the vision language model saw in the videos to what those causal rules said should have happened, right?
Bingo. That's the evaluation step. And by comparing those two things, they can assess how well the video generation model is aligning its output with the expected cause and effect relationships.
That's clever. So they're basically checking to see if the video is playing by the rules of the causal system.
You got it. And to really dig into a model's causal abilities, they break it down into 3 levels of consistency, each with its own set of measurements. First, there's text consistency. This is about whether the video accurately shows what was described in the text prompt in terms of those variables. They measure this with an all score, looking at all the variables, and a root score, focusing just on those initial root variables.
Makes sense. So you want the video to visually match what the text prompt is saying should be happening. What's the next level?
Next is generation consistency. This is about whether the model produces stable and predictable outputs when given the same starting conditions. So if you give it the same root variables, does it consistently generate videos that show the same effects?
So it's about making sure the model isn't just randomly throwing things together, but actually has some internal consistency.
Exactly. And they have a truth score here, which groups the videos based on what the prompt said should be happening with those root variables, and an observed score grouping them by what the vision language model actually saw happening with those variables in the video. Interestingly, they found that a lot of the models had pretty low generation consistency scores, around 0.1. They think this might point to what they call degenerative rules, where the model is basically outputting the same thing regardless of the input. Kind of like that feather example splash, no matter what.
Yeah, that's concerning. So basically, the model might be ignoring some of those root variables and just defaulting to a specific outcome. What's the third level?
The third one, and probably the most important, is rule consistency. This is all about whether the model is actually learning and applying causal rules that make sense in the real world. Similar to generation consistency, they have a truth score, comparing what happened in the video to what the ground truth causal graph said should happen, and an observed score, comparing what happened to what should have happened based on what the vision language model saw as those initial causes in the video.
Right. So they're checking to see if the model is following the rules, both according to the original causal system and also according to what it thinks it's seeing in the video.
Exactly. And what they found here was also pretty revealing. The average truth rule accuracies were below 60%, and observe accuracies were around 70%.
So not great. What does that tell us?
Well, it suggests that these models are having trouble both with understanding the rules themselves and with correctly interpreting what's going on in the text prompts. So even if the rules are right, they might be misreading the instructions, so to speak.
Interesting. So what happened when they actually put these models to the test with VACT? Did any of them pass with flying colors?
Well, not exactly. They ran this VACT benchmark on a whole bunch of current text-to-video models. The big names like Cogvideo, Videocrafter 2, Pyramid Flow, Hunyuan Video, Pika, Hailuo, Gen 3 Alpha, even Kling. And the results were, well, let's just say they were pretty consistently low across the board.
So none of these models really showed a good grasp of causal reasoning, at least according to VACT.
That's the takeaway, yeah. And this has some pretty significant implications. For example, that relatively low text consistency, hovering around 55-65%, it suggests that these models are having a tough time translating those textual descriptions, especially in complex or unusual situations, into the visual elements of the video.
Right. So even if they understand the concept, they might struggle to actually show it visually. And what about that low generation consistency, that 0.1 we talked about earlier? What does that tell us?
Well, it really supports that idea of degenerative rules, that these models might be learning to produce kind of fixed outputs instead of really understanding the relationship between the causes and effects. They're more like those if this, then always that systems, regardless of what this actually is.
So they're missing those nuances, those subtle interactions between variables.
Exactly. And those low rule consistency scores, they highlight that fundamental lack of understanding of how the world works, and that difficulty in following instructions, or at least interpreting them correctly.
So it's not just about the visual quality anymore. It's about whether these models can actually reason about the world in a way that makes sense.
Precisely. They even looked at different thresholds of certainty for the rules, and only a small percentage of them were learned with high confidence. And to make sure VACT wasn't just being too harsh, they did a human evaluation where people annotated causal systems, and the results were pretty much in line with what VACT found. So it seems like it's a pretty reliable way to assess this causal understanding.
Okay, so VACT is showing us something important here. But to really grasp why this is such a big deal, we need to talk about the history of text-to-video generation. It's come a long way, right?
Oh, absolutely. I mean, we've gone from those early JANs and VAEs, which were impressive at the time, to this whole new era of diffusion models. Models like Cogvideo, Levi, Videocrafter 2, Gen 3 Alpha, Hunyuan Video, Hailuo, Pika, Kling, and of course Sora. They've all pushed the boundaries of what's visually possible.
It's crazy how quickly things have progressed. But as these videos become more and more realistic, the need for better ways to evaluate them has become even more critical. We can't just rely on our eyes anymore. We need more rigorous ways to assess whether they're logically coherent and if they actually follow the laws of physics.
Absolutely. And there have been some attempts to do this before. VideoPhi and Feigenbench were important steps, but they often relied on a lot of manual work, and they weren't always great at distinguishing between true causal understanding and just picking up on superficial patterns. VACT is a big leap forward because it's fully automated and directly tests for causal understanding through those intervention experiments.
It's all about getting to that deeper level of understanding, not just the surface appearance. And this all ties into that bigger long-term goal in AI. Right? Achieving something closer to general intelligence, where machines can truly understand and reason about the world like we do.
Exactly. And this paper makes it pretty clear that even with all the progress we've made, these models still have a long way to go in that department. They're incredibly good at what they do, but they're still missing that crucial piece of the puzzle.
So let's zoom out for a second and talk about the big picture. What are the main takeaways from this research, and why should people care?
Well, the key message here is that the challenge in text video generation is evolving. It's no longer just about making videos that look good. It's about building models that understand the underlying physics and the cause and effect relationships of the scenes they're generating. And VCT gives us this powerful automated tool to evaluate that crucial aspect.
And what VCT is showing us is that despite all the visual advancements, these state-of-the-art models are still struggling quite a bit with causal reasoning. It seems they're relying more on those superficial correlations than on a deep, genuine understanding of how things work. And that ultimately limits their potential, especially if we want them to be those reliable world simulators we keep hearing about.
Absolutely. Think about the real-world implications. In robotics, if we're using these models to create training data and they don't understand basic physics, it could lead to robots behaving in unpredictable, even dangerous ways. Or in autonomous driving, if the causal modeling is off, it could mean crucial safety scenarios aren't being accounted for properly. Even in more creative fields, this lack of understanding can stifle the model's ability to come up with truly novel and plausible scenarios.
Right. It becomes more about mimicking what it's seen before rather than coming up with something truly new and original.
Exactly. But the good news is that the VACT framework gives us a way to systematically evaluate these models and guide future research toward building ones with much stronger causal reasoning abilities. This could involve developing new training data sets or using techniques like reinforcement learning to specifically reward models that get the cause and effect right.
And that brings us to our Novel Notions segment, where we like to toss around some ideas for future research inspired by the paper. And I have one that's been bouncing around in my head. What if we extended VACT to evaluate the counterfactual reasoning abilities of these models?
Oh, that's an intriguing one. Tell me more.
Well, imagine instead of just seeing if a model can show a splash when a stone is thrown, we challenge it with prompts like, generate a video of a stone being thrown into water, but it doesn't cause a splash. We'd be asking it to show us something that goes against our expectations of how the world works.
I like it. So by evaluating how the model handles these counterfactual situations, we could get a much better sense of whether it's truly grasping those underlying causal mechanisms or if it's just learned a bunch of associations.
Exactly. If the model still shows a big splash, even when the prompt explicitly says there shouldn't be one, it would be a pretty clear sign that it's relying on those superficial connections between stones and splashes rather than actually understanding the physics involved.
It would definitely expose the limitations of current models and their tendency to stick to those learned patterns. And this could be a really fruitful area of research, building on existing work in causal inference and counterfactual reasoning. There are already techniques like counterfactual regret minimization that could be adapted for this purpose.
That's a fascinating avenue to explore. And here's another thought. What if we could directly integrate this VACT evaluation into the training process itself?
Oh, that's a great idea. Imagine using those VACT metrics, particularly rule consistency and generation consistency, as part of a reward system during training. So the model would essentially be guided towards learning more accurate causal relationships.
Right, like if it shows that feather causing a massive splash, it gets penalized. And over time, it would learn to connect the properties of the object to the effect it has on the water in a more physically plausible way.
Exactly. The tricky part would be finding ways to do this VACT analysis efficiently during training, since it can be pretty computationally intensive. Maybe we could use smaller, more specialized vision language models for faster feedback, or even train a separate causal critic network that's specifically designed to evaluate the plausibility of the generated video frames in terms of cause and effect.
Those are some really clever workarounds. And if we could crack this, it could lead to a whole new generation of models that are not just visually impressive, but also grounded in a much deeper understanding of the physical world.
Absolutely. It would be a major step towards those reliable world simulators that have so much potential in various fields.
Okay, so to wrap up our deep dive today, this paper on VACT has given us a lot to think about. It's revealed some important limitations of current text-to-video models, showing that even though they're getting really good at creating realistic videos, they're still struggling with that fundamental understanding of causality.
And this is crucial because it highlights a need for more sophisticated evaluation methods beyond just how good something looks. We need to make sure these models are operating based on a solid foundation of understanding, especially as they become more integrated into our lives.
Couldn't agree more. And for those of you who want to dive deeper into the nitty-gritty details, you can find a link to the full paper in the show notes.
Always a good idea to go straight to the source.
And one last thought for you to ponder. As these incredibly powerful models become more commonplace, how do we ensure they're not just mimicking patterns, but actually reasoning about the world in a way that's safe, reliable, and, well, makes sense? Something to keep in mind as we venture further into this exciting and sometimes unsettling world of AI. Thanks for joining us today.
Until next time, keep exploring.